Physicists believe that when time began, at the moment of the Big Bang, matter and antimatter were created in equal amounts. And based on recent measurements made at CERN Laboratory in Switzerland, it seems there is perfect symmetry between the two, which they say implies that our universe should not exist. And theoretical physicist Michio Kaku. All right, Professor Kaku, so can you explain, first of all, what antimatter is and how is it different from the matter that we interact with every day?
Antimatter is the mirror image of ordinary matter. It's extremely rare. If I had some in my hand, it looked like ordinary matter, has the same chemical properties, except if I touch it, it would explode and destroy all of New York City, parts of Connecticut and New Jersey. Every Star Trek fan knows that this is the greatest energy source in the universe, matter-antimatter collision.
All right, so that's it. Well, what is it about this symmetry between matter and antimatter that, leads CERN's physicists to this conclusion that we shouldn't exist, the universe shouldn't exist?
Well, at the instant of the Big Bang, there should have been equal quantities of matter and antimatter, which annihilated, driving the Big Bang. So, by rights, we shouldn't be here. Because we have more matter than antimatter in our sector of the galaxy. We've looked for anti-galaxies. We've looked for anti-planets. We don't see any.
I don't even understand what that means, but okay, go ahead. Antimatter, anti-planets, because they would be made up of anti.
That's right. In fact, we see no evidence of that at all. So physicists say by rights we shouldn't exist. This means that at the instant of the Big Bang, there was a slight overabundance of matter over antimatter, and here we are as a consequence. Now, why? This is one of the greatest mysteries in all of physics. We are clueless to understand why. And like I said, if you want to win a Nobel Prize, figure this one out. Why was there's a slight overabundance of matter over antimatter?
All right. Well, tell us more about these experiments that CERN is doing to answer, or at least try to answer, these questions.
Well, they take an atom smasher and they take the energy out of it and put it into a bottle. It's called a magnetic bottle. You can actually trap anti-hydrogen, anti-electrons going around anti-protons. And when they measure the property of anti-hydrogen, it's exactly like ordinary hydrogen, except, of course, they would annihilate it if they touched each other. And that's so frustrating. You want to tear your hair out. They were looking for an asymmetry between matter and antimatter. They find none. And so that's the mystery. Why do we exist at all? By rights, we shouldn't be here. By rights, we should have been disintegrated at the instant of the Big Bang.
The apparent fine-tuning of the universe is one of the hottest and indeed most controversial topics in our intellectual life today. Among physicists, argue about it among each other, philosophers, theologians, and then philosophers, theologians, and physicists all together. I want to get your sense, first of all, about the legitimacy of the question in terms of, is the universe fine-tuned, particularly the initial condition?
Well, the universe is certainly fine-tuned in the sense that the initial state of the universe was extraordinarily special. Now, there's fine-tuning in the origin of the universe, which has to do with the second law of thermodynamics. It has to have been extraordinarily precise, and in fact, it has to have been at least as precise as 1 part in 10 to the power 123. Now that's a ridiculous
number.
It's a ridiculous number, yes. That's right. And it's nothing like, people worry about the constants of nature. You see, you want to fix those constants. Okay, they're just a few numbers, 20 numbers maybe. And those have got to be fixed to, I don't know, just a certain amount of precision. And that's nothing by comparison with this number. The precision that we see in the initial state of the universe completely dwarfs any of these other considerations.
And that level of precision is so impossible to conceive of as from some random point of view. I mean, that's not something that you can achieve in a random fashion under any. I mean, in infinity you can do anything, but obviously, but that's a.
It's no explanation. I mean, that's right. I mean, you can't say, well, there are lots of universes, and out of that particular one, which we happen to be in, that number was that thing. Well, no, it doesn't explain it. You don't get anywhere close to that number.
What is the implication then in terms of the generation of such incredible precision. Can the argument of multiple universes achieve that?
Well, I don't think any of these are going to, it's such an improbable. We're talking about how special the Big Bang was.
Yes.
Now, you could imagine other Big Bangs which weren't so special. But, I mean, you can have other Big Bangs not so special, but that's not what we've got.
Yeah.
You see?
And we're here in this one.
We're here in this one. We could have been here equally well in zillions of the other ones, you see, which weren't so special. You could have a universe which is special in our neighborhood. Our galaxy could be just as it is, but the distant universe would be different and not special out there. And that's much more likely. If you're just talking about probabilities, all these other alternatives are far more likely than the one we see, which is saying we're here and that's why the universe is as special as we see it, doesn't go anywhere to explaining the specialness of the Big Bang. It's just, it gets you nowhere because we don't need the universe to be that special for us. It's not any use to us at all why the distant universe is incredibly special and why it came from a Big Bang, which is just part of the Big Bang, which is just as special as the part we came from. And you can't say, another argument, you can't say, well, okay, you could have got lots more people by having a bigger universe. That doesn't work either, because there's lots of cheaper ways of making lots more people. You make lots of universes. And it's far cheaper in the sense of improbabilities, that's to say it's far more probable, to make lots of universes with a few people in each one than to make one universe full of people. And that's just a simple way of saying it.
In a sense, this is an even deeper mystery than the anthropic people normally put out for us.
Yes, it is, yes. No, it needs a scientific explanation. It needs a good physical theory to say why the Big Bang had that nature that it did. And we have no theory which really explains that. I mean, people usually say it's quantum gravity. No quantum gravity theory I've ever seen incorporates the asymmetry in time, which is necessary to explain why the Big Bang had this special nature and not the singular states which come from black holes, collapses, and so on. There has to be something asymmetrical, because the second law of thermodynamics is asymmetrical. And any quantum gravity theory which is going to explain why the Big Bang has this special structure has got to have that in it. And no theory I've ever seen has that character.
The physical universe operates mathematically. As Galileo put it, the book of nature is written in the language of mathematics. Scientists do not use mathematics merely as a convenient way of organizing the data. They believe that mathematical relationships reflect real aspects of the physical world. Science relies on the assumption that we live in an ordered universe that is subject to precise mathematical laws. Thus, the laws of physics are all expressed as mathematical equations. Isaac Newton's observations led to his discovery of the law of gravity, a mathematical relationship expressed as a simple equation that enabled us to enter the space age. And James Clerk Maxwell used mathematics to predict the existence of radio waves. Albert Einstein, working with theoretical mathematics developed 50 years earlier, formulated his general theory of relativity, a pillar of modern physics. His calculations were later confirmed during a solar eclipse, when Arthur Eddington observed light from distant stars bending around the sun. Then, Peter Higgs used mathematical equations to predict the existence of an elementary particle. It took 48 years, billions of dollars, and millions of man-hours for experimental scientists to finally detect the Higgs boson. How do we explain the astonishing applicability of math to the physical world? In 1960, the Nobel Prize-winning physicist and mathematician Eugene Wigner published an article that stunned the scientific community entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." Wigner concluded that the effectiveness of mathematics is a miracle, which we neither understand nor deserve.
You see, Einstein believed in another God, the God of Spinoza, the God of Leibniz, the God of order, harmony. The universe could have been random. It could have been chaotic. It could have been messy. But the universe is actually quite elegant, quite simple, and in fact is gorgeous. You can put the laws of physics as we know them on a simple sheet of paper. Amazing. Didn't have to be that way.